Hello everyone, this is part 1 video on past year NEET questions from the topic polymers. We'll start with a question that has come in 2019 paper. So this is a kind of memory based question. They're asking which of the following, so they're giving us 4 options to us. They're asking which of the following is a biodegradable polymer. Now what are biodegradable polymers? Those polymers that can be degraded by the biological activity. So in our syllabus, right, we have 2 examples for the biodegradable polymers. One is nylon 2, nylon 6, and the other one is PHBV. So these are the 2 examples we have for the biodegradable polymers. So nylon 2, nylon 6, right, it is a polymer of glycine which has got 2 carbons, and amino caproic acid which has got 6 carbons. That's how the naming for these nylon polymers comes, based on what is the number of carbon atoms present in the respective monomers, correct? So the nylon to nylon 6, right, it's a biodegradable polymer, and this is used for the stitching of the wounds, because after a while the stitches, right, will be degraded because of the biological activity. The answer for this is nylon to nylon 6. The other one, right, which is PHBV, is the polymer of 3-hydroxybutanoic acid and 3-hydroxypentanoic acid. So the PHBV, the full form is polybeta hydroxybutyrate copolymer with beta hydroxyvalerate. So this is another example for the biodegradable polymer. Next, we have a question that has come in 2019 Odisha paper. The polymer that is used as a substitute for wool in making commercial fibers. Generally, when we think about fibers, right, we'll talk about the nylons and rayons, but here we are talking about the particular application of the material used as a substitute for wool in making commercial fibers. Acrylonitrile, the homopolymer of this is polyacrylonitrile, which is what we call as also PAN in short. Okay, so polyacrylonitrile is the one that is used as a substitute for wool in making some of the important commercial fibers like Orlon and Acrylon. So these 2 names we can remember. So whenever we talk about making these Orlon and Acrylon, right, so what is the polymer that is used in making them? It is PAN or polyacrylonitrile. The answer for this is option C. Next, we have a question that has come in the NEET paper 2018. This is a kind of ambiguous question. We'll see what is the reason also. Regarding the cross-linked or network polymers. So cross-linked or network polymers, right, we also consider them as what? 3-dimensional polymers. Which of the following statements is incorrect? So what are basically these cross-linked or network polymers? So we'll have the polymer chains, which may be linear, like in most of the cases. Sometimes they may even have branching, and you will see that there will be a cross linking that will happen between these polymer chains, and that is the reason why we will be able to get the 3-dimensional network. And these cross linking bonds will be strong covalent bonds. The cross linking bonds will be strong covalent bonds. That's the reason why these cross-linking polymers, right, they will get the properties of hard and rigid nature in terms of their physical attributes. And the examples for this, we'll go through the examples in detail one by one. The examples are bakelite, melamine formaldehyde resin, and glyptol. Both bakelite and melamine are formaldehyde resins. And when we look at the formation of the cross-linking polymer, right, we are supposed to have cross-linking happening, which means generally if you have any monomer, it has got 2 functional sites or active sites, then it can give rise to the polymer chain. But if one of the monomer is having 3 sites, so one monomer is having 2 sites, other is having 3 sites, then this third active site which is left, that is what can give rise to the cross linking, and that's how we will be able to form the cross linking. So if you look at these options, right, option A is saying that they contain covalent bonds between various linear polymer chains. So I said the reason why this question is a little bit ambiguous is, yes, they contain covalent bonds between polymer chains, but in most of the cases the polymer chains are what, linear, but we also have examples where the polymer chain can be branched. So here they are specifically saying only linear polymer chains. So this is something that we might not agree completely. Option B is what, they are formed from the bi and tri-functional monomers. Yes, that is correct. And we will see when we go to the examples also, we will see how this will happen. Option C is saying that the examples are bakelite and melamine. Melamine means melamine formaldehyde resin. That is also correct. Okay, so here we are looking for what is the incorrect one. Option D is saying that they contain strong covalent bonds in the polymer chains. Yes, they do contain strong covalent bonds in their polymer chains. And in fact, what happens is, in most of the cases when we increase the temperature, right, the cross linking will also increase. As a result, what we see is that these polymers, they get hardened on increasing temperature, and that's how they become examples of thermosetting polymers as well. So we'll talk about it later, probably in another question when it comes, but this is about the cross-linked polymers. Now we'll just go through the examples. Look at bakelite. Bakelite is formed from the phenol and formaldehyde. So the formaldehyde has got two active sites. Basically the CH2, once the oxygen is removed, it is short of divalency, right? So that is how there will be two active sites. But the phenol, see where the linking is happening, to the carbons on the phenol ring, right? So even after the polymer chain is formed, so the polymer chain that is formed from the phenol and formaldehyde, we will call it as a novolac. This is the normal polymer chain, and we see that there are still the active sites. So these active sites can give rise to the cross linking, and that is how we will be able to get the bakelite. So bakelite will come because of the formation of the cross linking. So that is the reason why we said the cross linking will happen when you have bi and tri functional monomers. So here formaldehyde is an example of the bifunctional monomer, and phenol we can take it as example for the trifunctional monomer. Next we look at melamine formaldehyde resin. Here also formaldehyde has got two functional sites, means that CH2, right, of the formaldehyde has got two sites where it can bond. And if you look at the melamine polymer chain, the normal polymer chain, right, so the bonding of the CH2 is happening to the nitrogens that are attached to the ring. So we see here after the formation of the polymer chain, the third nitrogen is left as it is. Two of these nitrogens attached to the ring are used. The third nitrogen is left as it is. So this is the third site that is active, and that is what can give rise to the cross linking. So here we can see once the cross linking happens, right, one of the hydrogen from the nitrogen is removed, and that is what gives rise to cross linking, and that is how we will have the formation of melamine formaldehyde cross linked polymer. Again, glyptol. So glyptol, the monomers are ethylene glycol and phthalic acid. So the correct answer for this, right, I mean, because as we already discussed about the options, the option that we might want to choose, it's a little bit ambiguous question, but the option that we might want to choose is the option A, because they are here saying that there will be covalent bonds between linear polymer chains. As we said, there can be examples of branch polymer chains as well. Next we have a straight question based on the structure of nylon 6,6. So we see that repeatedly we have got questions based on either asking about the monomer to corresponding polymer linkage or the shape or structure of the polymers. So what is nylon 6,6? It is formed from the two monomers, each of them having 6 carbons. One is hexamethylene diamine, which has got 6 carbons, and adipic acid. So the CH2 groups, they have 4 carbons. 2 carbons, 1 from each of the carboxylic acid group. Totally this is also what, 6. That's how the name nylon 6,6 comes. If you look at the structure, right, between two NH groups there will be 6 carbons. Between two CO groups there will be 4 carbons. Now let's check the options. In option D, the chain, right, between two NH groups will have 6 carbons. Between two CO groups, look at what we have, CH2 twice, which means this is what, CH2 totally 4 times. And this is a polymer chain, so we cannot specify exactly what is the number of the monomers that will be present in a particular chain. So all these, right, so in fact here if you look at it, option A, they are saying 66, that is incorrect. This is also incorrect. So we anyway got our answer. What is it? It is option D. So the nylon 6,6, right, it's an important polymer that is used for making of the packing material, making of the sheet, combs, bristles, brushes, and sometimes it will be also used as a replacement for the metals in making of the gears and bearings. But what is the answer for this question? It is about the shape or structure of nylon 6,6, which is option D. Next we have a question on the natural rubber. Natural rubber has, they are talking about the cis and trans property of the natural rubber. So option A, they are saying alternative cis and trans. Option B, they are saying random cis and trans. Option C is all cis. Option D is all trans. So what is natural rubber? The cis form of 1,4 polyisoprene, right? That is what is the natural rubber that we obtain from the latex of the rubber tree. So the latex is the milky juice that we get from the rubber tree, right? So that will be in the cis form. So the answer for this is what? Option C. We also have one more form that is obtained from gutta percha. So this is important, gutta percha, right? The rubber that we obtain from the gutta percha, composition wise it will be same as natural rubber, but it will be the trans variety. Composition wise it will be same, chemical composition will be same, but it will be the trans form. Because of this, right, we'll see some properties being different. Like the natural rubber, it has got elastomeric nature. Of course, the elastomeric nature will be increased by vulcanization, but natural rubber also has got some elastomeric nature. But gutta percha, right, has very less elastomeric behavior. Elastomeric behavior means what? The ability of that polymer to get elongated. So the reason for this is the gutta percha is in the trans form and the natural rubber is in the cis form. So whenever we talk about the natural rubber, right, we are talking about the natural rubber that we obtain from the rubber tree. Next we have another question based on the linking of the monomer and the polymer. Caprolactam is used for the manufacture of. So caprolactam, right, it is the cyclic amide. So with 6 carbons, 1, 2, 3, 4, 5, 6. So why are we calling it as amide? Because it has got NHCO. So the caprolactam, when it is heated, right, it will undergo the polymerization, which we also take as an example for the step growth polymerization. And because the monomer, it's a single monomer, that's why we call it as what? Homopolymer. It's a homopolymer of caprolactam, that is nylon 6. So the reason why we don't have two numbers here is because the monomer is having only 6 carbons. This is a polymer formed from one monomer, that's why we call it as what? Homopolymer. Okay. Otherwise, in case of nylon to nylon 6, we have seen, right, in nylon to nylon 6 case, one monomer is having 2 carbons, other monomer is having 6 carbons. In case of nylon 6,6, one monomer will have 6 carbons, other monomer is also having 6 carbons. Okay. But in this case, right, caprolactam, when we heat it, right, it will undergo step growth polymerization to form nylon 6. But how do we prepare the caprolactam? From cyclohexanone, right, when we treat this with NH2OH, it will form oxime. Oximes undergo Beckmann rearrangement. This is something that we'll study in the nitrogen compound chapter also. They undergo Beckmann rearrangement to produce amides. Oximes will produce amides when they undergo Beckmann rearrangement. So the amide that is formed is cyclic amide here, that is the caprolactam. Next we have another question based on the biodegradable polymers. This is a question that has come in 2015 cancelled paper. The biodegradable polymer which can be produced from glycine and amino caproic acid. Already we have seen this, right? What is it? Nylon 2, nylon 6. So the monomers for the nylon 2, nylon 6 are what? Glycine and amino caproic acid. So here in glycine we have 2 carbons. Amino caproic acid we have 6 carbons. That is how the name nylon 2, nylon 6 comes. This is a biodegradable polymer that is used in making of stitches for the wounds. So answer for this is what? Nylon 2, nylon 6. You see here PHBB is also another biodegradable polymer, but the monomers for that are different. Next we have a question that has come in 2014. This is an interesting question. Which one of the following is an example for thermosetting polymer? So thermosetting polymers are what? When we heat them, they will get hardened. Already we said the cross linking or three-dimensional polymers, right? They are perfect examples for this. Why? Because on heating they would typically have more amount of cross linking that happen. As a result, because more amount of cross linking means what? More covalent bond being formed, and that's what makes the substance to get hardened. So the reason why I said this is an interesting question is because when we classify the polymers into the 4 categories based on the intermolecular forces or the response to heating. The examples here given, right? Option A, option B, option C, option D, they belong to each one category. Like look at option A, what is it? It is neoprene. So neoprene rubber is an elastomer. Typically most of the rubbers are what? They have elastomeric nature. They will get elongated. Option B is what? This is the PVC. So PVC is a thermoplastic polymer. Thermoplastic means when we heat it, it can be molded into whatever shape and form that we want. So PVC, polythene, all these are what? Examples of the thermoplastic polymer. Then option C is nylon 6, which is a fiber. Option D is what is this option D? It is the Novolac, which is the normal polymer chain of bakelite. So when it undergoes further polymerization or cross-linking, right, that is what will produce the bakelite. And bakelite is example of what? It is example of the thermosetting polymer. So when we heat it further means there will be more amount of cross-linking. That is what strengthens the polymer, and that's the reason why they become examples of the cross-linking polymers, right? They'll become examples of what? Thermosetting plastics. So the answer for this is what? Option D, which is Novolac. That is the shape that they are given is Novolac. That is the normal polymer chain of bakelite. When it undergoes cross-linking, that is what will give us the three-dimensional structure. Now we look at each of these types of polymers, the classification based on the intermolecular forces or the way they respond to the heat. So elastomers are what? They are the ones that will undergo very long elongation. So when we try to pull them apart, right, they'll try to get elongated. But once we release, like think about the rubber. Once we release, they'll be able to return to the original length. Okay. So in physics also, when you go to a chapter called as properties of solids, right, there you will talk about the behavior of the materials and how we will classify the materials into elastomers. So the reason why we are able to pull them apart is because the monomers are linked by the weak intermolecular forces, because only when the monomers are linked by weak intermolecular van der Waals forces, right, they can be pulled apart easily. And the examples are what? Most of these rubbers, like Buna S, which is the styrene rubber, natural rubber, that is the cis form. Then neoprene can be also called as what? Polychloroprene. Okay, so all these are examples of the elastomers. The second category is fibers. They are typically the rayons and nylons. They are very long, thin, thread-like polymers. They usually don't undergo stretching or deformation. Like nylon ropes, if you consider, right, they won't get elongated easily. And they will have high tensile strength because they will have strong intermolecular forces. The intermolecular forces will be what? Strong. Like the intermolecular forces can be the hydrogen bonding, etc. And they will also have crystalline structure with sharp melting points, because generally when a solid is having crystalline structure, the melting points will be sharp. Amorphous means the melting points will be staggered. The examples of the fibers are what? Rayons and nylons. Next we have the other two categories, thermoplastics. Thermoplastics are what? They get softened on heating. Once they get softened, we can mold them into whatever shape we want. Okay, and this heating and cooling, right? Like, we heat it, we can mold it, and then once it is cooled, it will have a different shape. The heating and cooling can be repeated number of times without affecting the polymer properties. Okay, so that is what will give rise to the ability of recycling. Okay, so what are the examples for this? Polythene, PVC. And when we compare the intermolecular force strength, right, they will be having the strength of the intermolecular forces stronger than the elastomers, but weaker than fibers. So if we compare the strength of the intermolecular forces, we'll have elastomers, which is less than thermoplastics, less than fibers. That is the order. Okay. Then the fourth category, where we'll have very strong forces. It's a three-dimensional polymer network. Okay. So the polymer networks that we have seen already, right? The phenol formaldehyde resin, example is bakelite, or the urea formaldehyde resin, all these cross-linking polymers, right? What happens is when we heat them, there will be excessive cross-linking that will happen. And because of this, we'll have more number of covalent bonds formed, and that is the reason why these polymers, they will get hardened. So once we heat them, means more number of covalent bonds are formed, and this cannot be reversed. So once the covalent bonds are formed, right, this cannot be reversed. So that is the reason why once you heat it, it will be hardened, and after cooling also, we'll see it will be what? In that hardened state, and this phenomena cannot be reworked or reversed. Okay, so that is about the thermosetting polymers, where we'll have strength of the intermolecular forces. Here we don't want to use the word intermolecular forces. Why? Because it is actually a completely covalent. So there is no concept of intermolecular forces. It is a completely, all three dimension wise, it is what? Covalent bonding that is there, which will be strong covalent bond. Okay, so this is about the four categories of the polymers based on the strength of the intermolecular forces or the way they respond to heating. Next we have a question that has come in 2014. Which of the following organic compounds polymerizes to form polyester dacron? So dacron is the commercial name for the polymer that is prepared from ethylene glycol and terephthalic acid. So ethylene glycol and terephthalic acid, when they undergo polymerization, they will be forming polyethylene terephthalate, which is also in short we call as PET, and that's where the name PET bottles comes. Okay, so the polyethylene terephthalate, right, can be also called as commercially either terylene or dacron. So these are used in textiles as well as in making of the PET bottles. So the dacron is prepared from where? It is prepared from the terephthalic acid and ethylene glycol. Option C is the right answer. So it's an example of what? So you can see the dacron, right? Why are we calling it as a polyester? Because so you have alcohol and this is what? Acid. When they undergo polymerization, they are forming what? Ester. It's a polyester. Next we have a question on the basic nature of the nylons. Nylon is an example of, already we talked about it. What is it? It's an example of polyamide. So we look at any of these nylons, like say for example we talk about nylon 6,6 prepared from hexamethylene diamine and then adipic acid. It has got 6 carbons. That's how the name nylon 6,6, right? So if you look at the nylon 6,6, what do we have? NHCO amide. Not only this, I mean, even if you look at nylon 6 itself, which is a homopolymer of caprolactam, right? So the polymer chain on this side, what we'll get? CO will come. So all these nylons, whether it is nylon 6,6 or nylon 6 or nylon 2 nylon 6 or nylon 610, okay, all these are what examples of polyamides. So this is about the part 1 video, and we'll see in the next part.